This resource is the first in a series on derivatives. We will explain the concept behind derivatives and formally define them. We will discover how to find the derivatives of various forms of functions, including polynomials and trigonometric functions. We will consider how to differentiate products, quotients, and composition of functions. We will also consider applications for derivatives and how they relate to real-world situations. A derivative is the rate of change for a function for any value in its domain. If certain conditions are met, this derivative can be found explicitly. For certain functions, it is easy to find the derivative. For example, if we consider the function described by driving with the cruise control set at 50 miles per hour, it is trivial to show that the rate of change is exactly that 50 miles per hour. In general, the rate of change for any linear function is simply the slope of that line. But what happens if the function is not linear? The rate of change for nonlinear functions are constantly changing. We cannot simply look at the equation for a nonlinear function and immediately recognize what the rate of change would be for a given value. Once we officially define the derivative, we will be able to determine this instantaneous rate of change. However, we need to build up to that concept first. What we can try to do is find a line tangent to the graph of our function, or one that only intercepts the graph once locally. Once we have this equation, we can find its slope, which will be exactly the rate of change for the function at that value. However, how can we find this slope? Let's work through a couple of examples and see if we can generalize. For example, suppose the intrepid mountain climber, MT Climber, stands at the edge of a canyon that is 2,500 feet above the canyon floor and throws a rock. We consider h, the height of the rock above the canyon floor, at t number of seconds after MT releases the rock. The path the rock flies through can be modeled by the equation h of t equals negative 16 t squared plus 96t plus 2,500. We wish to find out the speed of the rock 4 seconds after release. Until we formally define how to find derivatives, the only method we have for finding rates of change is to find the slope of a secant line. This means we will find the slope of a line that passes through 2 points on our graph, relatively close to the value we want. To do so, we find the function value for each of those points, subtract them, and divide by the difference between the time values. We will consider the times 2 seconds and 6 seconds after release. Finding this slope will give us an approximation for the rate of change exactly at the desired value. When we plug 2 seconds into the function, we find that the height of the rock is 2,628 feet. At 6 seconds, the rock is 2,500 feet above the canyon floor. When we find the slope of the secant line, we have the quantity 2,500 minus 2,628 divided by the quantity 6 minus 2. This simplifies to negative 32. It turns out that this is exactly the rate of change at time 4 seconds, due to the fact that the function is only quadratic. But what happens if we look at a higher order function? Suppose we have the function f of x equals x cubed minus x squared minus 8x plus 3, and we want to find the rate of change when x is 2. As we did in the previous example, we will try to find this rate by finding the slope of the secant line for points 2 units away from the target x value. In this case, we will use 0 and 4 for our x values. Plugging in to find the function value for 0, we find that f of 0 is 3. When we plug 4 into our function, we get a value of 19. Now we can find our slope. We have the quantity 19 minus 3 divided by the quantity 4 minus 0, which simplifies to 4. But if we look at our graph, it sure looks like the graph has a turning point at x equals 2. A line tangent to the graph appears like it would be perfectly horizontal, and therefore have a slope of 0. So how can we get a better approximation? What happens if we move closer to the target value of 2? What if we consider the values for x equal to 1 and x equals 3? Plugging 1 into the function, we get a value of negative 5. 3 yields a function value of negative 3. Finding the slope of the secant line, we have the quantity negative 3 minus negative 5 divided by the quantity 3 minus 1. This simplifies to a slope of 1. This is a better approximation, but can we do any better? What if we try 1.5 and 2.5? We plug in to get our function values of negative 7.875 and negative 7.625 respectively. Using the slope formula, we find an average rate of change of 0.25. To review, we realize that to find the instantaneous rate of change, we need to find the slope of the tangent line at that point. The slope of a tangent line can be approximated by the slope of a secant line, provided the values are close to the x value of interest. We also realize that the closer we are to the target x value, the better our approximation. This gives us the formal definition for the derivative. To find the derivative, we subtract the function value for x from the function value for x plus some value h. We then divide this difference by the value h. The derivative is what remains after we take the limit as this difference in x values goes to 0, or the distance between them disappears. This works so long as the limit exists. When it does, we say that the function is differentiable at that given point. For an entire function to be differentiable, we must be able to find this derivative for all values in the domain of the function. Note that there are two different notations for derivative which can be used interchangeably. The first is d dx, which means the derivative with respect to x. The second is f prime of x. We will look at a number of examples in future resources in this series on derivatives.